Welcome back to physics. We're going to start off today by going over your homework. So if you want to go ahead and get your homework out, go over the answers.
So question number 1, a dog runs into a room and sees a cat on the other end of the room. The dog instantly stops running, but slides along the floor until he stops by slowing down with a constant acceleration. Sketch a motion diagram for this situation and use the velocity vectors to find the acceleration vector. Alright, so to begin with, we're going to do the motion diagram. I'm going to use a particle diagram. So as he comes in, we have a dot right here. He sees the cat and he begins his descent until he comes to a stop. Alright, now it says use velocity vectors to find his acceleration. So if I did this correctly, I've got his initial velocity vector like this. The second one would be like this. So if I take this second velocity vector and I flip it around and put it head to tail with the first one, something like that, that will give me the overall acceleration, which is the difference between these two. So my acceleration would be that. The velocity time graph below is for Stephen as he walks along the midway at the state fair. Sketch the corresponding motion diagram complete with velocity vectors. So as we can see, he begins by having a constant speed. Now we don't know what the velocity is because there's no scale on the left side, but we do know that he has a constant speed. So at time of 1 second, he's here, time of 2 seconds, 0, 1, 2, then between 2 and 3 he decreased his speed down to half. Now that's a little bit harder to do because it's not going to cut my vector down to half. It's really only going to cut it down to about 2/3 or so because he's in the process of slowing down. If it were instantaneous change, then it would be cut in half. Alright, then he travels at that speed for 2 seconds, roughly half the speed of what the original was for 2 seconds. Then at 5 to 6 he slows down again, so we're going to cut down to about half here of what he's got. And then he stops, so he's going to be at the same point between the 6 and the 7 mark. And then between 7 and 8 he really starts to jump. So his average velocity during that time is going to be right around in here. And so I am going to make that a little bit longer than this section here, but it's got to be shorter than this section here. So we're going to go about right here. And then for the next 3 seconds, he is traveling at a high rate of speed. It's going to be longer than what we have in this original section here. So I'm going to make it like this. Alright. And so your diagram should look something like that. The velocity time graph below is of a toy train. When is the train's speed constant? The train's speed is constant right in this area here. I would say that's between the maybe 6 second and 13 seconds. The book has between 5 and 15. During which time interval is the train's acceleration positive? Well, it's accelerating during this interval. That's the only time it's actually accelerating in a positive direction. And so I would say between 0 and 6 seconds, your book has 0 to 5 seconds. And then part C, when is the train's acceleration most negative? Well, it's most negative in this location here. So even though it is negative throughout this time period, it's not the most negative. The most negative acceleration is going to have a steeper slope in a negative direction. So I would say from 15 to 20 seconds. In the graph, find the average acceleration of the train during the following time intervals. All right, so we're looking for the average acceleration. From the 0 to the 5-second mark, well, my average acceleration would be my change in velocity, which is from 0 to 10, so it would be ending at 10 minus the 0, and that's over this time period, which is 5 seconds. So I would say the average acceleration for part A is 2.0 meters per second squared. If we say this is 5.0, this is 10.0, and that's exact. From the 15 to the 20-second mark, so now we're looking at this portion here. Again, we're going to kind of estimate that it started out at 10 and went down to 4. So we have the final velocity minus the initial velocity over the time period, which is 5.0 seconds. That's going to give me a negative 6.0 over 5.0, which is approximately negative 1.2 meters per second squared. And then from 0 to 40, so during the whole time period, well, if we take the final velocity, which is 0, and we subtract the initial velocity of 0, and we divide by the 40 seconds, we get 0.0 meters per second squared. On number 5, they want us to plot a velocity time graph representing the following motion. So an elevator starts from rest from the ground floor of a 3-story shopping mall. It accelerates upward at 2 seconds at a rate of 1/2 meter per second squared, continues up at a velocity of 1 meter per second for 12 seconds, and then experiences a constant downward acceleration of 1/4 meter per second squared for the next 4 seconds as it reaches the 3rd floor. Alright, so I'm going to put time down at the bottom. The first thing I'm going to do is figure out how much time is involved. We have initially 2 seconds here, then 12 seconds here. That gives me a total of 14 seconds. And then we're going to have another 4 seconds here. That gives me a total of 18 seconds. So the end here is 18, making this 9. Alright, and then I need to come up with my velocity. And that's going to be in meters per second. I'm going up at 1/2 meter. My maximum speed is 1 meter per second. So I'm just going to make this 1 meter per second. That would be 1/2, that would be 3/4, that would be 1/4. Okay, so now I can do my graph. For the first 2 seconds, it increases at a rate of 1/2 meter per second. Now, that means after the first second, it is traveling 1/2 meter per second. After the second second, it's up to 1 full meter per second. It travels at that rate for the next 12 seconds. So from time 2 to time 14. And then it goes down by 1/4 meter per second squared for the next 4 seconds. So in second 15, it is going to be slowing down to 3/4. In second 16, it's going to be at 1/2. In second 17, it's going to be at 1/4. And in second 18, it's going to be at 0. We connect those points, and it should look something like that.
All right, we're going to begin our lesson today discussing positive versus negative acceleration. So here's a diagram.
What I'd like you to do is take a look at the diagram and describe what each of the following 4 situations, what is occurring. If we look at the first situation, you'll notice that we are beginning with a very slow velocity, and we're gradually speeding up. It's getting longer and longer. So in this first scenario, we would have what we call positive acceleration. In the second scenario, we begin with longer velocity vectors, and we end up getting shorter and shorter velocity vectors. So this would be a negative acceleration. Oftentimes we refer to that as deceleration. Now, in this third one, you've got to be careful, because this is the end and this is the beginning. So we start out with short velocities and end up with longer velocities, which means there is some acceleration, but to which direction? Well, if we're defining from left to right as the positive direction, that means this is still what we would consider a negative acceleration. Even though it's getting faster, it's accelerating faster in a negative direction. In this last scenario, we begin with long velocity vectors, and it gets shorter and shorter, which means we are decelerating, but we are decelerating in a negative direction. So it'd be like having the negative of a negative when you're adding. You end up getting a positive acceleration here. As another example, if we talk about free fall, which we'll discuss later, if I throw something up in the air, it's going to go up, reach a peak, and then come back down. If I define up as being the positive direction, as I throw the ball, I have a very high velocity. However, as it climbs further and further up, it begins to slow down. And so we would be decelerating, or we have a negative acceleration during those times. Once it reaches the peak, it is still accelerating in a downward direction. Well, that downward direction is considered to be negative because we defined up as positive. So accelerating in a downward direction would still continue to be a negative acceleration. So the entire time the ball is in the air, we have negative acceleration. Even though it's slowing down during this first half of its trajectory and speeding up during the second half, it is in a sense speeding up in the same direction throughout the entire piece, and that direction happens to be opposite of what I described as positive. Okay, so now that you've had a little bit of practice, let's describe what's happening in each of these lines. If east is considered the positive direction. So I want to point some things out here before you get started. First of all, 0 is located right here. That's my origin. Anywhere up is considered positive because that's the east direction. Anywhere down, which is the west direction, would be considered negative. Alright, so what is happening with A? You might say, well, A is not moving. But that would be incorrect because this is not a position time graph. This is a velocity time graph. Therefore, A is moving at a constant velocity. And that constant velocity is in an easterly direction because he's on the positive end. So we would say that A is moving at a constant speed, constant velocity, east. All right, now let's take a look at B. B is starting at a velocity of 0 and then is accelerating in an easterly direction or a positive direction. So for B, we would say it is accelerating from 0 east. Now let's take a look at C. C starts with a positive velocity, but then is moving down to a 0 velocity. So C is a negative acceleration, but he's still traveling east. Now let's take a look at D. D starts on the west side, which is a negative, goes all the way up, eventually hits 0, and then continues on. So D begins with a negative velocity but is accelerating in a positive direction and eventually ends up in a positive direction. And then finally we have E. Like A, it is traveling in a constant velocity, but it is a constant velocity in a westerly direction.
All right, so hopefully all of that made sense to you as we went through that. You do need to, again, make sure what type of graph you're looking at. Is it a position time graph or a velocity time graph? That tends to be the biggest error that students tend to make. So let's try an example problem. Here it says, describe the motion of a ball as it rolls up a slanted driveway. The ball starts at 2.5 meters per second, slows down for 5 seconds, stops for an instant, and then rolls back down at an increasing speed. The positive direction is chosen to be up the driveway, and the origin is at the place where the motion begins. What is the sign of the ball's acceleration as it rolls up the driveway? What is the magnitude of the ball's acceleration as it rolls up the driveway? Well, first of all, the sign of the acceleration, since we are dealing with acceleration, the acceleration as it goes up the driveway is going to cause it to slow down. So our acceleration is going to be negative because we defined up as positive, and since as it's going up, it's slowing down, that would mean that acceleration is happening in a negative direction. The second part, what is the magnitude of the ball's direction as it rolls up the driveway? So now they're wanting what is the magnitude of the acceleration. So our acceleration is the change in velocity over the change in time. Well, our change in velocity started at 2.5 meters per second, and we ended at 0. So if we take 0 minus 2.5, we get negative 2.5 meters per second. How long did that take to happen? Over a period of 5 seconds that was given to us. So if we take negative 2.5 meters per second divided by 5 seconds, we get negative 1/2 meter per second squared. Now, with sig figs, you are going to have 3 significant digits, so it would be a negative 0.500.
Okay, a race car's velocity increases from 4 meters per second to 36 meters per second over a 4-second interval. What is the average acceleration? So if we take our vehicle's final velocity of 36 and subtract our initial velocity of 4.0, and we divide by our time of 4.0 seconds, it gives me 32 meters per second divided by 4.0 seconds. That means my unit is going to be meters per second squared. And 32 divided by 4 is 8, and I do have 2 sig figs, so my final answer should be 8.0 meters per second squared. Now let's try number 11. If the rate of continental drift were to abruptly slow from 1 centimeter per year to 0.5 centimeter per year over a time interval of a year, what would be the average acceleration? So our final velocity would be 0.5 centimeters per year minus our initial velocity of 1.0 centimeters per year over our time frame of 1 year. So that gives me a negative 0.5 centimeters per year divided by the year, which is negative 0.5 centimeters per year squared as my average acceleration.
All right, and that concludes our lesson for today. You do have some homework tonight, so if there's still time in class, you can get started on that.